guys all have done that. You sat in there and made little lift-off noises, right? All right, that one holds 2 people. For Apollo, they had a spaceship that held 3 people. All right, so it was about 10 feet tall, a little bit taller than the average person, maybe about this tall. All right, maybe a little bit taller. All right, the 10-foot tall command module is this little tiny white triangle right here. Right here is the service module that held the environmental systems, the rockets that actually pushed the command module around in space after it got off of Earth's surface. And inside this triangle right here was the lunar module that they actually took down to the surface of the moon. So this was the actual spaceship that left Earth orbit and went to the moon. And this is what took to get it there. How in the world did that whole thing get lifted up off the surface of the Earth? Look at how huge that is. This is 10 feet. That little tiny thing, that's 10 feet. 10 feet tall. Probably about a little bit shorter than the ceiling to the floor. Okay? A little bit shorter than that. How did that whole thing leave the Earth's surface? Ellie?
Because like the fuel, all the gas that it takes, it like forces. I'm saying this wrong.
That's
okay,
right.
so the amount of force amount of force that takes for it to like lift off is the same. So it just kind of shoots up.
Okay, there's a whole lot of force. There's a whole lot of force. Gases are involved. That's absolutely true. There's a whole lot of force. It's eventually lifting off. Emmy, you want to add on to that and clarify?
The bottom half uses enough force and then it lets go and pushes off. They push off against.
I'm so impressed that you know about staging. Yes. This whole thing did not just all shoot up into the Earth's orbit. That's getting a little bit more sophisticated. But that's absolutely true. It would basically get to a certain stage. They would lose some of the mass by dropping it once all the fuel was gone. But, Jeffrey, did you want to add something?
The pressure from the engines comes down and hits the air, and the air reacts and goes back up.
Well then, how do they get to the moon? Because if they're up in space, there's no air to push off of. You guys remember the scene in Apollo 13 where they have to make a course correction on their way back to Earth? Otherwise, they're going to miss the Earth entirely and skip off into outer space and die? How were they able to make a course correction in space if they have a rocket and the exhaust has to push off of air?
Correct.
Philip?
Air molecule.
But there aren't any in space. Jack?
They bring oxidizer.
So they're making their own?
Well, they kind of bring their own air.
Right. The rocket pushes off of the exhaust that it sends out. There doesn't need to be any air because as long as it's sending out exhaust, which it has to if it's burning the fuel, that's what the rocket is actually going to push off of. So our action-reaction force pair, right, for Newton's third law, for every action there's an equal and opposite reaction. The rocket is pushing off of the exhaust, and it uses the exhaust to push off, right? The exhaust is pushing off the rocket in the same way the rocket is pushing off the exhaust, just in opposite directions. The rocket is sending the exhaust down, and the exhaust is pushing the rocket up, right? Yeah? Does that make sense? Okay. So, if that force that it's pushing up with is greater than the force that's pulling it down, which is what? What force is going to be pulling it down?
Gravity.
Gravity. So if that force pushing up is greater, then it's going to lift off. That upward force is called thrust. As long as our thrust is greater than the force of gravity pulling it down, we have liftoff. Anybody seen like a video or actually been to a launch? Probably haven't been to launches. I always wanted to go to one. I never actually made one. But when they start off, the rockets look like they're going really slow. You're like, how in the world is that thing ever going to get up into space? But as it ascends, it goes faster and faster and faster. All right. So, rockets and satellites. So, we've talked about rockets. That was kind of Newton's third law. What other laws? What other laws of motion do rockets depend on that Mr. Newton gave us? Emmy?
The second law and.
How? Emmy said the second law. What's the second law?
They have to have, it has to have force equals intensity, force equals mass times acceleration.
Very good. Force equals mass times acceleration. So if we're wanting to accelerate the rocket fast enough to leave Earth, do we know the mass?
Yeah, I know.
Yeah. You really need to make sure you know the mass because that tells you how much force you're going to need. Very good. All right, force equals mass times acceleration. What else?
Sorry if I go to the restroom.
Yes, you may. Is there another Newton's law? Let's see, we just said it's the second one. We said there's an action-reaction pair for the first law. I'm sorry, the third law. Ellie?
Is it the first law, the object in motion same?
Oh, very good. An object in motion tends to stay in motion, and an object at rest tends to stay at rest until when, Lee?
A force is applied.
Very good. An outside force is applied. What is our outside force that is moving our rocket off of the launch pad? The rocket's pretty happy sitting there on the launch pad. You know, it's hanging out. It's got frogs and bats on it. The thrust, exactly. The fire, the gas, the explosion, the controlled explosion that is liftoff. Very good. All right. So then we have satellites. Satellites are any objects that are in orbit around another object in space. We are on a satellite right now. We're on the natural satellite, that is Earth, orbiting around the sun. We see a satellite every night. Molly, what's that satellite we see every night? Not the ISS, because we don't see that every night.
Moon?
Yes, exactly. The moon orbits around the Earth. That is a natural satellite. There are also, so you can see, and warning, this is not to scale. The Earth traveling around the sun in orbit is a natural satellite. And then we also have artificial satellites, right? ISS, all of the satellites that help us with our cell phones and GPS. Anyone know what this satellite is? Jack?
Hubble?
It is Hubble. I remember watching them. Actually, we would watch it during class when they did the repair missions in the early 90s on Hubble. So that is the Hubble Space Telescope. Rest in peace. All right, so circular motion. You guys were using circular motion when you were swinging your yo-yos around, right? Was it accelerating? I heard some people saying that their object was going at a constant speed. Was that yo-yo accelerating, Olivia? If it was going at constant speed?
Well, technically it could because it's changing direction.
Oh, I'm so happy you remembered that. Yes, absolutely. What are our 3 ways of accelerating? Elizabeth?
Changing direction.
Changing direction.
Speeding up and slowing down.
Yes, exactly. We can accelerate by speeding up, slowing down, or changing direction. So, that yo-yo was constantly changing direction, so it was constantly accelerating. If something is accelerating, it has to have a force acting on it, right? An object in motion stays in motion. An object at rest tends to stay at rest. If it is constantly accelerating, it is constantly having a force put on it. What is that force that is making it change direction? You can look up there. You can. What do you think, Dalton? Centripetal force, exactly. Raise your hand if you've heard of centrifugal force, right? So centripetal force, we're going to talk tomorrow about how centrifugal and centripetal are 2 totally different things. Usually, when you guys are talking about force in a circle, you're talking about centripetal force. So, here is, who spun the yo-yo around your finger? All right, so here's your finger. This is the rotation of the yo-yo around your finger. And then here, what is this showing? Right, the yo-yo's direction, the yo-yo's orbit. Right, here's our circle. It is traveling in a circle around your finger, so the yo-yo was in orbit around your finger. Here's our string. Here's the yo-yo. What do we notice about the force that's on there? Katie, what do we notice about that force that's on that yo-yo?
That it was going like
force because it was the hand, like circle going to go around.
Okay, it's not actually coming from the hand. Your hand is what's spinning it around.
Would it
But-
be the string?
Absolutely. Your hand is pulling on the string, which is then going to be pulling back on your hand. But, so that's right here. There's our action-reaction pair. But the force is also going to travel down here. So the string is pulling on the yo-yo, and the yo-yo is going to be pulling back on the string. There are two action-reaction pairs when you're making your yo-yo orbit around your finger. So Katie is absolutely right. The centripetal force is actually provided by the string, which makes sense because look, the string is pulling on the yo-yo, it is pulling it towards your finger, right? Everybody kind of observed that? All right. What about the velocity? What direction is our yo-yo going in? What do you think, Gabe? Okay, and granted it's kind of difficult. So here's my question. If I did not have Miss Hunn's very superior Duncan yo-yos over there, if I had gone to the Dollar Tree and gotten, 10 yo-yos for $1, and they were really cheap and the strings all broke while you guys were spinning them and they all clocked each other on the head, how would the yo-yos travel once the string broke? If I'm spinning my yo-yo around like this, the string breaks, is the yo-yo going to go whoop? Matthew? Alright, what if I was like this when the string broke? What direction would it go? Yeah, right. It would go right for me. Is that up, but it's left for you guys, so yeah, I see that. Right, it's going to continue in the same direction it was going once that force was no longer accelerating it back toward the inside of that circle, back toward the center, back toward your finger. So it's going to go in a straight line, right? If I had taped something to one of those fan blades, and over time, the tape wore off, is the object going to continue going in a circle? No. It's going to go in whatever direction it was going once that tape baked. Alright? So that's what centripetal force is. So, if I had let you guys lasso that yo-yo around the top of your head like this guy, we would have the centripetal force provided by the string, and then the yo-yo going around in circles, and then once you let go of it, or it breaks, it's going to continue in the same direction. So, no matter where the yo-yo or object or satellite is on the orbit, and these little circles are the satellite's position at each time, the centripetal force is always going to be pulling it in towards the center, and the velocity is always going to be going at a right angle to it. Does that make sense? Here's our 90-degree angle, our right angle. Alright, so the string provides the centripetal force for the yo-yo. What is providing the centripetal force for a satellite? Do we have a lot of strings attached to the satellites and they go around the Earth? Hannah? Would it just be the Earth? What about the Earth? Because the Earth is a mass, it's not a force. The Earth does have gravity, as a matter of fact. Unfortunately. I didn't get to take off. Alright, yes, the centripetal force that is always pulling the gravity, the satellites back down to Earth is gravity. What made my ball fall and hit the ground? Well, now wait. You guys can't have it both ways. You're telling me that gravity is keeping satellites in orbit around the Earth, but then you just told me that it made my ball fall and hit the ground. How can the same force, how come we don't have to carry like lead umbrellas around to protect ourselves from falling satellites? Alright, Emmy?
Because in space, I'm talking about in space, right? In space.
Tell me why am I not worried right now about a satellite hitting me in the
Well,
head?
in space, I guess it's equal.